In this video, we're going to take a look at how we take the derivatives of natural log of u of x and a to the power u of x. So these guys are special. They don't fall under our regular derivative rules. It's a small extension of the chain rule that we'll use for both of these guys, but we could have kind of written these formulas pretty much at any time. They just kind of show up in this section in the textbook, so that's where this video is coming from here. So what I want to do is look at how we take derivatives of these types of functions here. So these don't correspond to power rule. We have a to the u there. I want you to think about like e to the x. Same basic idea that we have with a to the u. It doesn't fall under the power rule umbrella. So we just have to be a little bit careful with that. It's got its own special derivative. The derivative of natural log of x, we have to be 1 over x. Okay, and it's not super obvious where that comes from. You'd have to go back to that limit definition. And I've got in parentheses there that x has to be positive, okay? And that's because natural log function only exists when x is bigger than 0, okay? So the derivative then has to correspond. We generalize this with the chain rule, and we say that the derivative of natural log of u is 1 over u times u prime, or u prime divided by u. There it's of course taken to mean that u is a function of x, and I've written that for us up here. So that's typically how we'll treat the natural log function, where we find its derivative. We look at the inside. What's inside our natural log function, does that have its own derivative? If it does, then I'm going to be thinking about u prime, the derivative of that inside function. Let's look at some quick examples here. The first one I have for you is natural log of 2x. So I'll take a derivative of this guy using my newly learned derivative rules for natural log. And I see very quickly that I don't just have x on the inside of my natural log function, I've got 2x. Okay, so that's a function of x, and it's got its own derivative. Okay, the way I typically work through these is that I go just like I would any other composite function. I go outside to inside. So I say that the derivative of natural log of something is 1 over the something. Okay, and then of course I have to multiply by the derivative of the something. Derivative of 2x is just a 2, and that's what I have there in pink. So I usually write this like 1 over the inside, 1 over 2x, times the derivative of the inside, which is 2. We can quickly see that this simplifies. The 2's cancel, and I'm going to end up with just a 1 over x. In fact, we can say that the derivative of natural log of any constant times x is just going to be 1 over x, okay? And we can show that by some quick properties of logarithms. We'll get to that. The second one I want to show you here is the derivative of natural log of x squared plus 1. This one I'm going to handle just basically the same way, but again, I quickly notice that x squared plus 1 has its own derivative. So I need to incorporate that as a chain rule step. That's going to be like u prime. So again, I quickly see that this is going to be like u prime over u, where the numerator has a derivative 2x. Then the denominator here should be just what u is, what that inside function is, x squared plus 1. So that's quickly just using this formula here. And you know, you can go through it as I did example A, but many of these we can quickly kind of then zoom past the pieces parts and go right to kind of what that final derivative form would be. Let's do another one. Derivative of natural log of x quantity cubed. Okay, so here I've got natural log of x times itself 3 times. Again, chain rule here is going to prevail. I've got an outside function, so when I take a derivative of that outside function is something to the third power. So I bring the 3 down, subtract 1 from the exponent, and leave the inside the same. Okay, so I've got 3 natural log of x all raised to the second power. Times, chain rule, derivative of the inside, derivative of natural log of x is just 1 over x. Okay? So these aren't so bad. They're just their own special set of derivatives, right? They don't fall under the same rules as we've had so far. The chain rule still persists right through all of this, so just be careful. I alluded a little bit to using properties of logarithms, and in fact, those are going to be something that we can use to our advantage when we take derivatives. So these log properties can be extremely helpful. Let's look at an example. If I were to take the derivative of this logarithm of a really nasty quotient there, I've got x times x squared minus 3 all squared, and then I'm dividing all of that by the square root of 2x cubed minus 1. Okay, so as it sits, if I were to take a derivative of this, I would do the derivative of natural log of something, so I would get like 1 over the inside, 1 over the fraction there, and then I would have to take the derivative of that. I'd have to do a big quotient rule. It would be very cumbersome, time-consuming. So instead, what we do in situations like this is we use properties of logs to our advantage. Okay, so what I do is I've got log of a quotient here, log of a quotient, and in the numerator of that quotient I have a product. We're able to break apart that product by the sum of the logs of the product, right? So what we'll do is we'll take that numerator and we'll break it apart, and we'll write it like natural log of x plus natural log of x squared minus 3 all squared. Okay, we can break apart the log of a product as the sum of the logs there. The quotient part we'll be able to write as subtraction. So we'll be able to say that this is minus natural log of the square root of 2x cubed minus 1. Okay? So I've used log properties to my advantage here to help me write this in a more manageable way. I can take derivatives a bit easier when I've just got individual components like this. There's one more thing I can do. You'll notice that the second logarithm there has a power, 2, and the third logarithm does have a power as well, 1/2. I can take the log of something to a power as bringing that power down in front, okay, down in front and multiplying the logarithm. So what I'm able to do here is write all this as log x plus 2 times log x squared minus 3 minus 1/2 times log 2x cubed minus 1. So again, that's another property of logarithms. I know it looks like power rule, but it's not there. That's just a property of logs that I'm using to bring that exponent down in front. From here, I can then finally differentiate. I can find my derivative because I've written these in such a way that kind of all the log properties I know that are helpful are exhausted. So now I've got just kind of basic logarithms that I'm going to take the derivative of. First one, derivative of natural log of x, is going to be a 1 over x plus derivative of 2 times natural log of x squared minus 3. That 2 I can leave alone, and then take the derivative of this natural log piece. Derivative of that natural log of something is 1 over the something, 1 over x squared minus 3, times the derivative of the something times derivative of x squared minus 3 is a 2x. Okay? So that's the derivative of a log of something, log of u, times u prime, the derivative of the something, minus 1/2 times the derivative of log of 2x cubed minus 1. So I've already written there the derivative of the inside. Derivative of the inside is 2x cubed. Derivative of 2x cubed, is 2 times 3x squared, or 6x squared. I left it as 2 because I noticed that 2 is going to cancel with the 1/2 I have out front. I'm going to write that in the denominator as 2 times 2x cubed minus 1, right? So that's 1 over the inside, 1 over the something, 2x cubed minus 1, times the derivative of the something, 6x squared, and I get a cancellation there. So all I've got here, when I collect like terms, is 1 over x plus 4x over x squared minus 9 minus 3x squared divided by 2x cubed minus 1. Okay, there's my derivative of that complicated log function that I had, but again, this is a situation where we'll use logarithms to help us out. Okay? This is something we'll revisit in the next section, when we're talking about implicit differentiation. So keep those log properties close. They're going to come back for us here. So I've got derivative of log of x, or log of something, log of u, and a to the u I still have to do. But what about other bases, right? So far, natural log of x has a base of e. That's log base e. We're also able to take the derivative of e to the x. Well, what if I've got something like a to the x and I want to take a derivative of that? There's a nice little way that we can derive these formulas here without using our limit definition, just the derivative rules that we already know. So take a to the x, and I want to take a derivative of that. I'm going to rewrite this in such a way that I can use what I already know, so that I can use e. We have some properties of exponents and logs here to be able to write that this is the same as the derivative of e to the natural log of a. E to the natural log of a is just a. So that all reads a to the power x. Okay? But this benefits me now that I know chain rule, because I have the derivative of e to a power. Derivative of e to the power is e to the power times the derivative of the power. So that power there is natural log of a times x. That's a constant times x. So the derivative of the power is just the constant. Okay? Kind of simplify a bit. E to the natural log of a, remember, is just a. So this guy I can write as a to the x then times natural log of a. So this is my derivative of a to the x. A to the x natural log of a. Okay? Of course, if I've got not just a to the x, but say a to the u, then I can write this as a to the u natural log of a, but I just have to remember to take the chain rule there. The derivative of the exponent would be a u prime. Okay? So that's not so bad. It's a little bit abstract. It's a different formula to kind of remember. A lot of the times you'll be working with things like 2 to the x or 3 to the x or something raised to this x power that we'll have to take the derivative of. So it's not so bad. What about then y equals log base a of x? We've done log base e. Log base e is, of course, the natural log. But in general, we hope to be able to take the derivative of any logarithmic function. So we're used to log base 10, right? Just a general logarithm. But we might want to be able to take the log base 2 derivative, something like that. There's a clever way to do this as well. We do what we call change of base. We can write this as 1 over the natural log of a times the natural log of x. You might have seen this before as natural log of x divided by natural log of a. So that is what we call a change of base formula, and because we know the derivative of natural log of x already, we can use this to our advantage. Similar to what we just did with a to the x, natural log of a is just a constant. So 1 over the natural log of a is also a constant. When we go to take our derivative here, y prime, we have the constant, 1 over natural log of a, times the derivative of natural log of x. Derivative of natural log of x is 1 over x. Okay? So there's our general formula here. We just rewrite it. Typically it's seen as 1 over x natural log of a. And again, I want to be able to write this in general. Derivative of log base a of u is 1 over u times natural log of a, but of course times then u prime. Okay? I'll just do a quick few examples here. Let's take the derivative of 2 to the x. Derivative of 2 to the x, that's like a to the x, is a to the x times natural log of a. That's all there is to it. That's just straight kind of memorization with that derivative rule. Another, let's take the derivative of log base 10, that's just a regular logarithm, log base 10, of 7t squared plus 3. Okay, so this one's more involved. I'm going to have some chain rule. I'm going to have the derivative of the inside as 14t. So I'm going to write that right away. But again, log base 10 here is what I'm taking the derivative of. So the derivative of the outside function, log base 10, is 1 over natural log of 10 times the inside. Right? So I do 1 over the inside, 1 over log base 10 times the inside, times the derivative of the inside. I did that first there. Derivative of 7t squared plus 3 is a 14t. Okay? That's all there really is to it. All right, so it'll take a few practice problems to get through and get a feel for those 2 or 3 new formulas that we've got. Derivative of log to any base, derivative of natural log of x or log of u, and then a to the x or a to the u, where we have a different base than e. Okay, so these all have their own special formulas. I encourage you to write them down, but we can add them now to all the other derivative formulas that we know. So in fact, I'm going to bring up, there's a nice little table they have at the end of this section in the textbook that looks like this. I have it there for you. And it's all the derivatives we know written out. Okay? They've got the chain rule there set up as just, one kind of specific formula. There's my chain rule. And what I advise you to do is actually take all of these formulas, or many of them, and write them with the chain rule embedded in them. So for example, this derivative of sine of x, you might write that as the derivative of sine of u. Take a derivative with respect to x. So incorporate the chain rule in all of these, right? Kind of like they did with the generalized power rule there. Okay? So that's a good technique to use. You should also, make flashcards if that works for you. That's something that, can be very useful to try to help memorize all these different formulas. Some of them look a lot worse than they actually are, right? The constant rule, the derivative of a constant is just 0. We know that. We apply it all the time. Writing it down makes it look cumbersome, but it is. It's there, and writing it down like that can help with that exposure and being able to memorize it that much better, that much easier. That's all for this video. Thanks for watching.